Hi, so this video is on scalars and vectors, which is a math topic. So to kick us off, we're going to look at a AI scalar and vector joke. Let's see, we're going to do scalars and vectors into our teacher jokes. Let's see what AI comes up with. Why did the vector break up with the scalar? Because it couldn't handle a relationship that was only one-dimensional. I don't know if that's funny or not because I don't know what a scalar and vector is. So maybe we need to revisit this after we know what scalars and vectors are. All right, so without further ado, we're going to follow this handout here. I do want to point out that scalars and vectors is part of AP Pre-Calculus. It's actually in Unit 4, which is for Hinsdale South only in the BC version of AP Pre-Calculus, unfortunately for those of you who did not see that in Pre-Cal. So we're going to give you a summary of this stuff so that we're ready to go. This is Unit 1.1 right out of the gate in AP Physics C in terms of us having to know this for math. Having to know this for physics is going to be really important. So scalars and vectors are simply labels that we can give, or categories we can give to quantities. Every variable that we have is going to be categorized as either a scalar or a vector. So we need to contrast what these two are. A scalar is going to be any quantity that's just a number value. There's no direction to it. It's just simply a number. In math, we often refer to a scalar quantity as being a magnitude. It's just like a number value. So examples of this that we can measure that are scalar quantities, or the variables are scalars, would be time, mass, temperature, energy. None of those have a direction. They just accumulate over time or throughout a problem, right? So key number one would be for this, one of the things I want to use as my contrasting here is that when you have a scalar, the positive or negative value is simply the same that you would have if it were on a number line. So for example here, the number 2 and the number -5 on a number line would imply that 2 is a higher number, right? It's just a bigger number on a number line. And that's the case for all scalar quantities. Think of temperature, 2 degrees Fahrenheit is going to be bigger than -5 degrees Fahrenheit, a higher temperature, right? Now a vector quantity, if the variable that we have is a vector, then it also is a scalar, but we add another layer to it, which would be its direction. So it's both a magnitude and a direction. So it adds an extra layer onto scalars. So the key thing with vectors is this concept of an arrow. That's really almost like synonymous. It's a hallmark of a vector is that it has an arrow with it. So if you think from a diagram standpoint, if we can draw a variable as an arrow because it has a direction, then that quantity is a vector. So diagrams are going to be huge for this, vector diagrams. We can show the magnitude often by the length of the arrow. Sometimes we do, if in case like you have a grid right here, then we may be showing the length of the arrow to represent how strong, longer or stronger. Or we may just draw a diagram where we're not really not focused on, the actual length, like a scale drawing of how long it is, but just drawing a direction. You've seen that a lot in freshman honors physics. In this example here, we do like a force diagram, which you did a lot of. If there's a grid, then that allows us to do, for example, an arrow that's 2 boxes long. And this arrow is also 2 boxes long, and we've labeled those variables, those arrows with a variable like this. And so what we can show if we're doing a scale drawing for those arrows, since they're the same length, they'd be the same strength. And therefore we could say that they would have the same value or equal values, right? We could also do that with unbalanced forces. So for example, if we had a force tension and a force of friction, and the tension was supposed to be larger, then I could show that since it's 2 boxes and friction's 1, that would imply that we have tension greater than friction. And that would create an unbalanced net force, if you can remember that from freshman year. So we don't have to just do forces. This is just simply an example. We can do this with any quantity that has a direction we can draw as an arrow, and that we would refer to as a vector quantity. It is very common for AP Physics C to give you these grids as part of a problem and ask you to diagram different vectors that they tell you to do. They're going to use that grid for you to compare 2 different vector quantities like we did here with different forces, to show if they're equal or unequal in magnitude. Just as a notational thing, since we have these variables, these letter variables that we use all the time in physics and math, if we want to make sure that we're tagging a variable as being a vector as opposed to scalar, then we can put a little arrow over that vector. So for example, delta x, velocity, acceleration, force, those are all examples of vector quantities. And so by putting an arrow, we're saying, hey, just so you know, it's really important that we're treating this as a vector. We can still just put f, and it's implied that it's a vector. But again, if you want to like tag it that this is important to treat as a vector, then you can put the little arrow over it, and that's saying that we're calling it out, kind of highlighting the fact that it's a vector in that problem. So it's important here to realize that vectors, as we said, have both a magnitude, its number value. This is often treated as an absolute value, so it's just how much how strong is that value. And then the direction is going to be represented by the positive and negative. And it gets a little bit more tricky here when you have multiple dimensions, but at least along some axis, if you have a positive value for a vector, then it would be along the positive axis. If it's a negative value of that vector, for example, -5 as opposed to +5, then that just tells me that the arrow is pointed along the negative direction of the axis. What makes this confusing, potential pitfall that we have here is think about how this would compare with a scalar quantity, right? If you have a positive or negative vector, and that positive or negative, it represents the direction, the way the arrow is facing along the axis, positive or negative. Then if we go back to our example of 2 versus -5, we would actually say that -5 is a larger magnitude because we're going to be treating it as having an absolute value of 5. It would be, for example, in our grid, 5 boxes, but just pointing to the left in the negative direction. Whereas a different arrow that was pointing to the right might be only 2 boxes. So 5 boxes is greater than 2 boxes. So with that positive or negative representing direction, it creates a potential point of confusion when you compare vectors and scalars. A third key for scalars and vectors is that when we're taking a measurement, like how far, for example, we can take that as being a scalar or a vector in some cases. So for example, sticking with the how far, I can measure that as just a distance that doesn't really care about the direction. So if I'm looking at how many miles I'm putting on my car, I don't care which way I was going, north, east, south, west. It's just the mileage that your wear and tear that your car is experiencing, right? So that would be a scalar version of how far. That's what we refer to as distance. Distance is the scalar version of how far you go. If we look at how fast you're going, and we stick to the scalar quantity of that, again, like I don't really care what direction I'm heading, north, east, south, west. I just want to know how fast. Then we'd be getting speed, and we can calculate speed by using the distance you travel over time. That would give us the average velocity. The distance you would travel, like let's say from point A to point B, does not need to be a straight line. It would just simply be the overall distance traveled if I were to figure out how long that blue line is. Displacement would be how far, but with an arrow. So it has to be a straight line arrow because it's how far with a vector, meaning it's got a number value and a direction. So from point A to point B, we'd be looking at then a straight line distance from point A to point B. And the average velocity from point A to point B would essentially be that displacement. Like how far did you end up from where you started? How far is point B from point A? What is that just straight line distance? And we could represent that again with an arrow. So here, it doesn't matter what path we took, it's just simply comparing an initial location, or what we call initial position, to an ending or final position or location, which we have as point B. We can also represent vectors because they have both a magnitude and a direction in a number of different ways. And this is going to be important to note because math is going to tend to use this first version that we can refer to as a component form, although since math pretty much just uses the component form, they just call it vector notation. So unfortunately, that's going to be possibly a point of confusion if you're thinking back to math. But the component form, although you won't hear that label, it'll look familiar because you'll have seen that a lot in pre-calculus and calculus. What AP Physics is going to use more are these last two that we're going to go over, which would be unit vectors and the polar form. So let's take a look at what we're dealing with here. So if we have component form, this is again what you're going to use a lot in pre-calculus and calculus when they refer to as vector notation. Then we have to look at, well, what happens if there's a 2 dimensions or even 3 dimensions if there's a z-axis? So we need to list then the x and the y components of that within a bracket. Okay, so for example, if we have point A to be the origin and point B ends up being up here with some coordinate x, y, then what is the vector form or way in which we can label this, like display this? So obviously I could say that this vector r, which is a straight line distance from point A to point B, can be described as being in brackets in component form x and y, meaning how far I move x along the x-axis and how far I move y along the y-axis. I can also do this with functions. So, for example, if x was changing as a function of time and y was changing as a function of time, then r would be changing as a function of time. We deal with this a lot in what we call parametric equations too, if that rings a bell, and that would be projectile motion. But anytime we have these this vector notation we can have obviously constants for x and y as being just fixed values, or we can have it changing the time. Unit vectors are what we're going to use instead of the components that are written in brackets. So we're going to take again that x and y, and we're going to write them, but with unit vectors. So I know that pre-cal is aware of this, and they're going to try to explain this if you do have this unit in pre-calculus. So let's take a look. Same exact situation. We're starting at the origin, ending up at some point x, y, and I want to express then that vector r, which is how far from point A to point B, but with unit vectors instead of components. So what we're going to do with this is we're going to then say the vector r can be described as whatever the magnitude of x, which would mean how long is x, like how many meters that is, for example, or meters per second that is along the x-axis, whatever that number value is, we're just going to multiply it by I with a little caret on top. We call that I hat. Anything that's multiplied by I hat is going to be along the x-axis. Likewise with y, if we take whatever y is, whether it's a function or in this case it's just some constant value, let's say it was just 4 meters, right? Then we just multiply it by j with a caret on top, which we call j hat. And that means anything that's multiplied by j hat is going to be along the y-axis. The math reason for this and why they're called unit vectors is the variable I hat is a magnitude of 1. So when you multiply anything by 1, it doesn't change what you have for x because x times 1 is x. But it has a direction to it, which is along the x-axis. So now when you take this value and you multiply it by 1, along the x-axis, then you're making whatever this value is directed along the x-axis. And likewise with j hat and the vertical axis. We can also do this with functions, so anything we put inside the parentheses here and multiply it by I hat is simply going to be directed along the x-axis. And anything that we put in the parentheses here and multiply by j hat will be directed along the vertical axis. So we can do x as a function of t, multiply it by I hat, so we know that it's along the x-axis, and we can do some function along the y-axis and make sure we multiply that by j hat, so we know that that's going to be directed along the y-axis, and we can treat them separately. Polar form would be probably what your brain would attach to this right away, which would be right triangles, because this is in fact a right triangle. So if we just wanted to know what is the hypotenuse, the magnitude, the length, right, of the hypotenuse, then we would have to be using right triangle trig. So we'd want to say like, okay, well, what is the absolute value of the hypotenuse? So the absolute value of vector r. And then to give it its direction, we would use its theta here. So we can get the magnitude of our hypotenuse, meaning the magnitude of the actual vector, in this case r. Again, we can replace r with any variable, v or a or force. But we can get the magnitude by doing Pythagorean theorem. And then we can get the direction of this, which would be expressed as the angle theta, by doing a second tan or arctan. We need to keep in mind that we have to use our right triangle trig here sometimes to define x and y in terms of r and theta as well. So we can use those to, I think of it as converting between unit vector or component form where it deals with x's and y's, or the legs of the triangle, into its hypotenuse and angle. It's kind of the conversion is what I would think about it. Now, which one do you want to use for your problems? I would just stick with the one that's most convenient for you because polar form and unit vectors are both on equal grounds in terms of expressing them as answers. So if you just stick with one that makes the most sense, for example, if it wants to know the magnitude of a vector, then I probably want to use Pythagorean theorem here and do it that way. If I'm working with the x and y axis separately as I solve the problem, like we do with projectiles, where you look at the vertical motion separate from the horizontal motion, then I would probably just leave my answer in unit vector form instead of taking all these extra steps to try and then convert something that's already done, right? If I have x and y, I can just list it with I hat and j hat, and I'm done. I don't need to do Pythagorean theorem and arctan to get the angle. All right, thanks. I hope this helps. Let's go back to our joke now. So let's look at joke one. Why did the vector break up with the scalar? Because it couldn't handle a relationship that was one-dimensional. Oh, that's hilarious, right? The vector has a direction. And yeah, okay. What do you call a vector that tells jokes? A puncture. That's terrible. Why did the scalar get kicked out of the party? Because it couldn't find the right direction. So AI is not sophisticated enough to be telling jokes very well, so that's okay. Have a good day.